3, 2, 1. All right. Welcome to yet another Math 2070 online video. Today, we're going to introduce a infamous but very useful computational tool called the determinant. All right, so let's determine it, shall we? Okay, so for a 2x2, the determinant is the following magic number. So every 2x2 matrix has an A, a B, a C, a D like this. And the magic number is AD minus BC. And that number is hopefully familiar to you because we saw that number appear when we were talking about the formula for the inverse of a 2x2 matrix. So I wonder if the determinant is going to be related to that concept. All right, so for a 2x2, right, this magic number we have encountered, and so it makes sense to sort of isolate and talk about it. So notationally, we'll use det of A to denote the determinant, and if we have our matrix written out, we typically will put vertical lines around it rather than our usual box for the matrix to represent that we're computing the determinant of this. All right, so for a 2x2, this number has appeared, and we have seen it useful, and hence we should give it a fancy name. But this, of course, let's, of course, do some computations here. Pretty quick and easy. So note for A, B, and C, A, we've got the product of the diagonal minus the product of the off-diagonal. So 1 times 4, the AD. And 2 times 3, the BC, and taking the difference, giving me a -2. Similarly here, 5 times 9 minus 3 times 3, 36, and here we see a magic determinant of 0. Nice. And hopefully if you get your peepers out, you can immediately tell something about this matrix. It's not invertible. The columns are not linearly independent. So, all right, and furthermore, note that we have got a negative, a positive, and 0, so we've seen that. All right, seems like the determinant doesn't really have any rules as to what value it could take. All right, now, of course, we've computed these before when we were trying to find inverses of 2x2 matrices, but this, of course, all of it leads to a kind of natural question. All right, well, what would the determinant of a 3x3 be? Right, as we talked about, for getting the inverse of a 3x3 matrix, we didn't get a formula for that. We had an algorithm that said, well, if you do this, you'll find the inverse. All right, but is there a magic number for 3x3s like there is for 2x2s? So let's just detect invertibility and somehow let us compute the inverse. And then for 4x4 and beyond, is this possible? Can I do this? Well, the answer is, hopefully not surprising, yes, there is a determinant for a 3x3 and a 4x4 and a 5x5 and beyond. Note they're all square matrices. But there's a lot of computational front-loading we need to do before we get to the actual, determinant. Okay. So, for an n-by-n matrix, where n is strictly bigger than 2, the minor M sub jk, that's the notation I'm going to use for minor. It's different from the notation our book uses, but I like this one better. So the minor M sub jk is the determinant computed after deleting the jth row and kth column. So note for a 3x3, I can compute the minor for this. That would give me, right, delete a row and a column, it gives me a 2x2. I know how to compute the determinant. The cofactor is this quantity where we look at m sub jk, the minor, and then multiply it by -1, where we've raised that to the power of j plus k, so we'll have minus signs sometimes and minus times other times. So that's what the cofactor is, and of course if you're asking, hey, why are we doing this? Yes. So, the cofactor expansion across the jth row is then computed by getting all of your cofactors and the jth row, so C sub j1, C sub j2, up to C sub jn, and multiplying them by the corresponding entries in the row. So note this kind of looks like a dot product. So that's the cofactor expansion across the jth row. And similarly, the cofactor expansion across the cave column is formed by, instead of going across the row, go down the column. All right, so obviously we have all these sort of mechanisms here. We have all this mechanical machinery, and a natural question that you're asking is, why are we doing any of this? Well, it takes a little bit of effort, and we're not going to get into the details, but it turns out that cofactor expansion across any row or any column is always going to produce the exact same number. And that's what we'll call the determinant. And, of course, you might be asking, well, why do we do any of this? Why are we deleting rows and columns? Why are we sometimes multiplying by -1? Why does it matter? Why doesn't it matter that it doesn't matter what row and column we go through? All of these things have answers that become apparent once we actually just start playing around with these formulas and seeing examples of them, and then sort of the why of everything kind of pops out. So for now, we're just going to take face value that, yep, these are computations, these computations are good, and they give us the proper value of something called the determinant. And as we go through the sequence of videos on determinants, all of this stuff kind of gets answered for us. All right, so for now, though, this is how you compute the determinant of anything bigger than a 2x2. It's recursively defined. To compute a 3x3, you perform a cofactor expansion across a row, which involves computing determinants of 2x2s. And then you can imagine the nightmare that happens once we have a 4x4. Well, then you do a cofactor expansion across a row. That then gives you a bunch of determinants of 3x3s, which you then have to cofactor and get determinants of 2x2s. So computationally, this becomes incredibly complicated very quickly. But as we'll see, as we've kind of already noted, there's theoretical tools here that are very useful and very powerful, hence why we want this stuff. All right, but talk is cheap. Let's actually compute a bunch of cofactors and minors for our matrix A here, and then we'll use that to arrive at the value of the determinant. Okay. So here I've computed all of the minors, and again, the M11 minor is obtained by deleting row 1, column 1, and computing the determinant what's left over. So if you do that, if you delete row 1 and column 1 of our matrix here, then we've got 5, 6, 8, and 9 as the 2x2, and there you see the determinant of that 2x2. Likewise, the minor 2, 1 is delete row 2 here and delete column 1, and then take the determinant of what's left over. And what's left over will be the 2, 3, 8, 9, and that's the determinant that you see right there. Likewise, the minor for 3, 1 is delete row 3, column 1, and then you're taking the determinant of the 2, 3, 5, 6, 2x2, and that's that value right there. And then you go down the line and get all the minors. So this is a good time to pause the video and do these computations yourself and make sure that I know what I'm doing. Always a good check. All right. And there you go. Pretty cool. All right, so that's computing all of the minors. Now, the cofactors are then found by slapping in minus signs. So, for example, here this is a plus, this will be a minus. This is a plus because it's entry 1, 1, so it's -1 squared. This will have a minus because it's -1 cubed. This will have a plus because it's -1 to the 4th power, so on and so forth. But as you can see, we start with a plus and then alternate plus and minuses as we traverse left to right, top to bottom. So plus, minus, plus, minus, plus, minus, plus, minus, plus, right? Because all of them are negative to begin with. All right, and then the determinant can be found by taking the cofactors and multiplying them by the entries of either the rows or the columns you're going down. So here I've done it across row 1. So this one corresponds to the entry 1, so we multiply it and add it. This corresponds to the entry 2, so we multiply and add it. And this corresponds to the entry for 3 here, so we multiply it, add it all up, and hilariously, we get a determinant of 0. All of that work just to get nothing. The mathematician's classic trick. All right. There you go, so we have now officially computed the determinant of a 3x3 using the cofactor expansion. Right. Now, note, in general and in practice, you don't need to compute all of the minors and all of the cofactors. You just need to do them for one row or one column, whichever one you pick. I just wanted to demonstrate all of the computations here for you. And in particular, when you are doing your cofactor expansion, because it does not matter which row or column you pick, you should always pick one where there, are a whole bunch of zeros or a bunch of nice numbers. So for example, here is a 4x4, but something hopefully immediately jumps out at us. Column 2 has a bunch of zeros. So what I want to do here is the cofactor expansion across column 2. So column 2 here we're fixing and going down. And note that if we go down it, the cofactor expansion will delete all these other terms except for the entry here in the first row. And note that this is plus minus, so I'll have a -3 times the determinant of delete the row in the column and what's left over, which is 641, 723, 138. And so then we have to compute the determinant of 641, 723, 138. And in order to do that, well, this one, we don't really have anything too advantageous, so just pick row 1. That's usually what I like to do. Go down the entries. Note that it's plus, minus, plus. So here I've got positive 6, minus 4, positive 1. Take the determinant of the matrix found by deleting the row in the column, and here we get a negative 151 for the determinant of that 3x3, and then we float back and note that the determinant of A that I'm looking for is -3 times that, giving me a determinant of 453. All right. There we go. Computed the determinant of a 4x4. And as you can imagine, you can go for 5x5s and beyond. Note that the 4x4 I did an example of was computationally quite nice because there were a bunch of zeros. A similar sort of matrix will show up on maybe a problem list, I don't know, and maybe some homework, I don't know. All right. So we've defined how to compute determinants for any size matrices. We've seen that there's a lot mechanically going on, so a lot of opportunities to screw up some plus signs or minus signs or mess up a multiplication. So obviously we're going to want some tricks. We're going to want to have some easily computable determinants. Okay. And it turns out that certain matrices have very easily computed determinants. We've already encountered the lower triangular matrices when we were talking about the LU factorization. We can also have upper triangular ones, and basically these are matrices where the only non-zero entries are above or below the diagonal. And for any such matrix, it turns out the determinant is just going to be the product of the diagonal entries. Nice. All right, and so for example, it's pretty easy to verify the matrix A here. It's going to have a determinant of 1 times 3 times 6. You hopefully can immediately see that, because if we cofactor expand on row 1, you'll have 1 times the determinant of this 2x2 in the corner, and the determinant of the 2x2 in the corner is 3 times 6. And a similar thing happens when you cofactor on, let's say, column 1 here on the matrix B. So pretty easily computed for A here, which is a lower triangular matrix, and B, which is an upper triangular matrix. And as a nice, neat little consequence of this, let's conclude by noting that the identity matrix has a very easy determinant. Its determinant's 1. Nice. All right, so there concludes our brief little introduction of what determinants are, how they are computed, and our first little taste of a matrix with a relatively easy to compute determinant. All right, so naturally now, with all of this said, we're going to want some more techniques to help us out with determinants, and that'll be what we'll talk about in the next video.